All right, good morning. So today's topic is very important because we are going to discuss something called Ethernet, and all of you are using Ethernet at this point in time. Okay, apart from internet. So you should know what Ethernet is, right? All right. So if you want to read more, you can go to these resources. So these are the contents, these are topics that we'll cover today. Okay, so last class we discussed about layered architecture. And we have seen that first three layers, that network layer, link layer, physical layer, is there everywhere. So all, even the end nodes, suppose you have your computer, for example, and server, and in between their routers. All of these will have these three layers: physical layer, link layer, network layer. All of them will have these, and they will interact with. Only at the end we have application and transport layer. Okay, application will run only at the end, so obviously it has to be at the end. Okay, and note that both if this side some application is running, other side has to run the same application, otherwise they can't interact. And then transport layer is here in both. Then this transport layer says that whether we want reliable service or unreliable service, and then IP layer on top of below this is common. Okay, so now these three layers are responsible for communication of data across or through all the nodes. Okay, all right. Only at the end we have these two layers, transport and application. So security, although we say that has to be at the end, but we'll have to do something to secure even bottom three layers. So we'll discuss what. Okay, so now we see that these two layers are among the first three layers, which is there in all the nodes. These two layers change depending on the link, whether it's a Wi-Fi, which so basically medium is air, or Ethernet cable, which could be category 5, 6, 7 or whatever, and or it could also be satellite. For that, link quality changes, hence the protocol. Protocol involves how two ends will communicate with each other. Okay, that also changes. Okay, but the network layer remains the same. So if you, so what happens that as application generates data here, okay, that will get encapsulated in a transport layer packet. Okay, that will have some ports, which basically it has to say which application will receive this data, and also whether reliability is required or not. And this packet goes inside Ethernet packet, sorry, network layer IP packet. So this becomes a payload of IP packet, and IP packet goes inside Ethernet packet. It is shown here. This is application data. Okay, now you're using TCP or UDP. So this packet is formed. Okay, when it goes further down, this becomes the payload or actual contents of IP packet. So this is IP packet. This is a header which will say about source, destination, etc., etc. Where header here will tell which port we are using, which application is using it, whether reliability is required or not, some sequence number or whatever. We'll look at that later. And then all this stuff goes inside a link layer, because IP packet is being formed and it will traverse over different links. Okay, so now if we put this inside another packet, or we call it frame, now layer 2 we call the packets are called frame, and then this will also have source address, destination address, and what kind of data this contains and all that information. So now this all will go from one end of the link to other end of the link. Let's assume this is Wi-Fi. Okay, at this point, after receiving, this portion is removed. Okay, and then IP packet is given up. Okay, up means that higher layer, then that will see where the packet to be sent to. Okay, it will decide the path. If there are multiple paths, it will decide one of the paths and then find out what quality of the link it is, what type of link is. Suppose this happens to fiber, then this will be put into another layer 2 frame, and IP packet will come here. Like example we have seen in case of a mother sends laddu to you and then it passes, right? So these are the links. This is the first link, second link, third link, and so on. All right, so this is what we studied. Now let's look at link layer. Simplest link layer technology is where we have just a piece of wire, right, at two ends. So we can use multiple protocols for that. We can use Ethernet. Okay, like from your machine, if you put Ethernet cable up to router, there's just simple link, right? Or you can use PPP, or there are many protocols at layer 2. So what we are interested in is in Ethernet. Now Ethernet here does not say that only two ends of a wire. Okay, it says that multiple machines can be connected over a piece of wire, right? So like this is a piece of wire, or sorry, a wire, and then we can connect multiple machines like this. Okay, like this diagram that's shown here is the original diagram which Metcalfe has designed. When he was thinking how to connect multiple computers in a room or in building, then he came up with this idea: run a wire all across the building, and then different computers can be connected through this kind of probe. It will just attachment. So when I started working initially, I was part of a lab in IT Delhi. Then first time emails were used in the country. Okay, and later on, when we laid the thick Ethernet cable in ITM, then we had laid this kind of cable, which ran all across building. Okay, department building, and everyone's room will be connected through this kind of probe. Okay, now you'll have to actually dig a hole, and it's very so instrument used to, some specific instrument was used to connect this probe into the wire and so on. Okay, so this was a technology. Create a small hole and attach a wire to this one, or probe to this one, something like this. Now from this, Ethernet has grown, and we'll see how it has evolved. But Ethernet has become de facto standard for layer 2. So now when we think of layer 2, we usually talk of Ethernet, because Ethernet is not only local area networking technology, but also it's become wide area networking, because it's just a framing method where IP packets can sit. Like most of your IP packets right now, or my IP packet that's reaching to you, are going over Ethernet, even over wide area network, like from the cell tower to, from here, for example, from here is going to my router, which is connected to fiber to ISP. Now from my router to ISP is going up, most likely is going over Ethernet. Okay, but right now in our discussion, we'll keep our discussion simple to the local area network, or LAN. When we say local, it means that local within a building or a room and so on. Okay. Now physical media for Ethernet is changing also, right? It started with unshielded twisted pair. This is cheapest kind of pair, which is not non-shielded. There's no shield here to reduce interference. It's not there. Now then came shielded twisted pair, where this kind of pair, this kind of shield was used to reduce interference. Okay. All right, but this is expensive, so not in use. And people found that UTP, unshielded twisted pair, is usually good for most of the application. So within that also there is a started a cat 3, category 3, 4, 5 is the most popular. So most of our needs are met with 5, and now almost up to cat 8. So quality is improving, and hence the speed. Okay, and then came why do you need this kind of wires? Why not use fiber? Now fiber cannot be used this way, right? You can't just take out signals from a wire. It can work with metal only, right? Copper. So some different techniques were used. We will come to that. Basically switched Ethernet. Okay, and then last type is Wi-Fi, right? Wireless, Ethernet over wireless. Like what I am using right now is I don't have Ethernet, this kind of cable. Okay, most laptops don't come with this kind of cable. In fact, my laptop is 80 years old and has not come with the Ethernet port. Okay, so it's connected to my router with Wi-Fi. Okay, this is called wireless LAN or wireless Ethernet. Okay, all right. So this is the evolution of Ethernet. It started from, as we said, this something called thick Ethernet, which we studied earlier, and then now as now note that this is unshielded twisted pair UTP, and as improved, then speed also improved. Like it's like, for example, we can in 2010 only we could get 100 gigabit per second Ethernet or 40 gigabit Ethernet using category 8 cable. Okay, and now of course we have switched Ethernet, so we can use fiber, which can go up to 100 gigabit per second. Now, in fact, there are experiments of 400 gigabits per second. This technology is there, but not many people are using it. Any question up to this point? Okay, all right. So let's look at Ethernet frame format, right? So note that we have seen that as packet moves from layers, finally there is Ethernet packet, right? Ethernet frame. So we'll have define, and every packet or frame will have header, which will say how to treat this and what is here, right? Okay, so for example, when your mother sends laddu box to you, she will write something on top of the box, right? From is not that important. To destination address, source address. Okay, and also if she, instead of laddu, if she is sending you, say for example, glass, some tumbler or pieces of glass, then she will say that inside, handle with care inside glass, right? Something like. Similarly here, what is inside has to be defined. Okay, so these are some minimum fields, but this becomes a payload where IP packet will come in. Complete IP packet, which will also contain source, destination, etc. That becomes payload for Ethernet. All right, so we'll define what is this format, what is the header, and what this contains. Okay, so this is the format. Now the something where IP packet will sit is this one. Okay, so IP packet will come from top and will come here, and all others are kind of extra information that's required. Okay, header or tailor, right? So now let's look at what are these things, right? And these are, we call all this as a control information, something that's extra to carry this data. Okay, now something, now note that after this packet will directly go into wire or air. Okay, so there has to be some, and you have studied digital electronics, right? Okay, and you know that clock, see, you can receive a signal, digital signal, if clock at both ends are synchronized. Okay, like you're sending, like signals like this. At the other end, it has to be sample this to read, that says a 1, this 1, and so on, right? 0, 1, and so on, right? So the clock, if the clock at both ends are not synchronized, you cannot read anything. So there has got to be something to synchronize clocks, and this is called preamble. Okay, it's a sequence of bit sequences which will train clock recovery circuit. Now we cannot go into details of this. Please read it from any book if you're interested. Then start of frame delimiter, it indicates the start of frame. Like, if you're receiving laddus from your mother, laddus are inside, but on top of that there is a box. So this will say that now inside is laddus, right? So there is a boundary here, which is a cardboard box or polythene sheet or whatever. Okay, so this will similarly here, this a bit, it will define uh, it will define what that now from here the frame starts. Okay, so it's a 1 byte. Okay, and then there's a destination address of 6 bytes, which is 48 bits. And source address, who is sending it, again 6 bits. Then there is a type field, which is 2 bytes. Basically to say what kind of data is inside, whether there is IP packet or IPX or it's something else. That anything can be inside depending on the protocol. Ethernet doesn't say that only use IP, but IP has become kind of de facto standard, but it can carry anything, right? So what is content inside, like your mother will say inside laddus or inside glass or inside whatever, right? Jalebi or whatever. This will help, the one who receives it to take care of it and interpret it that, like, in that way, right? Okay. Now, if it says that inside is IP, the packet will go, at a receiver end, it will be sent to an IP protocol, code corresponding to IP protocol. Otherwise, it will go to something else, right? Okay. Then there's something called data, which is actually data. Okay. Then pad is required, some extra number of bits, because Ethernet says the minimum size of the frame has to be something. Okay. Ethernet will not work if the size is very small. So if the packet, the number of bits that you are sending is just few, then it will pad it with extra zeros. Okay, and so that's the reason this pad is used. And then cyclic redundancy is checked. Basically, if you one or more bits are in error, it can find it out. Okay. All right. So all these like CRC, pad, and preamble, start of frame delimiter, etc. If you're interested, please read it from the book. Will not go into details. Ethernet address is usually 48 bits. Now, many people can argue that it's not 2 raised power, or 2 raised power, yeah, I mean, what? It's not 2 raised power x, where x is integer, right? But it's how it's designed, right? 48 bits people thought is good enough. In fact, it's coming out to be true that 48 bits are generally good enough to cover, the usage. IP address was 32 bits at that point in time, IPv4, that was not sufficient. Anyway, so we can, in general, if you see what Ethernet address is shown, is like this, like when you have, so every laptop will have Ethernet card. Okay, it's called MAC address. Okay, similarly, any mobile phone will also have MAC address. So it's basically address of interface card. Okay. Now, when you receive your laptop, you buy a laptop, it comes out, so basically when manufacturers make it, they give it a unique number based on some understanding between different manufacturers and some governing bodies, right? So every machine has a unique MAC address. Okay, is burned into network interface. Okay, like Ethernet card, if you buy, earlier time we used to assemble our laptops, sorry, desktop, then we'll buy Ethernet card. In that card, this number will come east, burned into, right? Now, of course, if you want, you can change this Ethernet number by programming. Like in data centers, we in order to ease routing, all these numbers are well defined in a sequence. But nevertheless, if you look at Ethernet address of, if you have 2 laptops, check whether Ethernet address are different. So you'll find it's different until unless you have changed them. Okay, it is globally unique, of course. Now it's globally unique, so now routing can be done. or okay, but note that it does not have a structure, accepting that structure which can help in routing. Okay, it's kind of flat addressing. Of course, part of this manufacturer given by manufacturer, part of this is based on something, but in general it does not have intelligence built into it which can help in the routing. So it's a kind of flat addressing. So now if you say that can I do routing from my room to somebody in USA, can it be done? No, it cannot be done, because you know you have 2 raised power 48 destinations. Okay, and you'll have to create, and there's no hierarchy here, right? So you have to, your table has to be, routing table has to be this big, which is quite big. You cannot do it, and you'll have to get the numbers from everywhere, you know, and so on. So it's an impossible problem to solve, right? Then Ethernet, we can do unicast or multicast. Part of multicast is also, type of multicast is broadcast. I hope you understand. Unicast is one-to-one, one source, one destination. Multicast is one source and there are some destinations, like say 5 destinations. So one source to say some number of destinations. Say this is D1, D2, D3, D4, D5. This is multicast. And broadcast is one source to all destinations, right? Okay. So now Ethernet supports unicast and broadcast, or we also call it sometimes multicast. Okay, so any question up to this point? No? Are you able to understand?
No, sir. It's clear.
Yeah? Please focus. I am going very fast because normally Ethernet is covered in 2 or 3 lectures. And we don't have time. Actually, this is a bonus lecture for you, right? Because you guys, it's very important for you to understand Ethernet, right? All right. So this was the first one we discussed, right? Thick Ethernet. And it had its own problems, right? What happens if this becomes faulty? Okay, then the whole network will be disturbed. What happens if somebody cuts this? Because all exposed. Okay, so this will again, and then the what can be the length here? It's all restricted, right? It's just 500-meter maximum. Then next generation came, instead of having this kind of structure, why not move a wire across multiple machines? And this inside machine will be a card. Okay, that was called thin Ethernet. So it came sometimes around 1980s. Okay, sorry, I started with this, then moved into this one. And now issue here was that what happens if this machine is faulty? Machine itself is a faulty, because it's not passive piece of equipment, right? It's an active piece. It basically it has to be switched on. Machine has to be switched on, right? And then this was very popular for some time. This was popular for a few years, and then came this method. Then people thought, why not? Every machine, every laptop has to run a wire up to a central piece, which is called hub. Okay. Now, if you look at it, and these are cheap wire, this is called twisted pair, which we have studied earlier. It's a very inexpensive, and this method is called 10 base T, because 10 was the maximum speed, 10 megabits per second. Okay. Now, what happens here? If you look at it, there's no difference between, technically no difference between this one and the one here. Is if you collapse this into a single node, then it becomes a point here. So this is nothing but a repeater of a signal. Whatever signal it gets, it just amplifies and sends it to all. So essentially same as this one. Okay. So now started with this, okay, and then the packet or frame will have at least three things: source, destination, data, that we have already studied, and use a protocol called CSMACD, which we will study now. And even Ethernet use this CSMACD, but it hardly comes to part of it hardly, the feature of that is hardly utilized, but still as a mandatory part it runs. So, and nevertheless, so we'll study CSMACD considering this architecture, right? Okay. All right. And these protocols, now note that this is a shared medium, a piece of wire, right? Okay, and machines are connected to this one, and so on. So it's a shared medium. Okay. All right. So now we have to run a protocol, right? All these should run a protocol, and this is a distributed protocol. When we say something distributed, means each machine has to run the same protocol. Now it's based on very intuitive idea, very simple idea, like that we use often in life, right? So in a class, when there is a silence, then teacher talks, right? Or anybody can talk. Okay, similarly here, when there is, so each machine senses whether a communication is happening or not, and any machine finding out silence, if there is silence, can start transmission. Okay, now like I am communicating now, okay, and then after some time I find that I am successful in communicating and nobody has spoken at the same time, then I will continue to speak. So now if this guy signal reaches to the end and nobody has started, even the last guy has not started communication, okay, then when I will come to know about it that nobody is speaking, when my signal comes back here, so I will wait for 2 times propagation time of my signal to end, because signal will take some speed, right? It will go with some speed, it will go to the end, and if there is a collision, if there is somebody starts communicating, then I will come to know only after when this collided signal comes back. So I will wait for 2 times propagation time and we'll know that nobody has started communicating. So now I can continue my communication. And if I find like when likewise, like when I'm talking here and anybody starts talking, then I will come to know that the collision. Okay, then I will stop. Everyone will stop. And then after again some time, we'll start. Okay. So that's the reason this protocol is called carrier sense. Every machine has to sense whether there is a signal or no signal, or there is a silence or no silence. Multiple access, multiple machines can access it, and collision detection. Each machine should be capable of detecting collisions. Okay, all right. So now let's look at the protocol. Very simple. So each machine is connected with NIC, network interface card. Okay, let's not worry about it. Like your laptop has a NIC, network interface card, right? NIC receive datagram from network layer. From higher level, it will get a packet, okay, and creates a frame. So IP packet, so okay, this is IP packet. It will create a frame, okay, and then NIC senses a channel. It will sense the wire whether there is a the signal or not. If it's idle, if there's nothing, then start frame transmission. Then it will start transmitting the frame. If it is busy, then wait until channel becomes free and then transmit it. So when I'm talking, obviously you will not talk, okay, and when I stop talking, when there's a silence, then you can ask question, right? Okay, if NIC transmits the entire frame without collision, then NIC is done with the frame. Okay, all right. If NIC detects another transmission while sending, like a machine starts sending transmission here, it initially finds channel is free, it will send signal, and then at this point this guy also starts. Before this signal reaches to this guy, okay, when signal reaches to this guy, then it will know something is there, but just before that it starts communication, so there will be a collision. Collision means a change in voltage signals and so on, and this collided signal will go both ways, right? Okay, all right. So if collision is detected, everyone will become silent. Everyone will know that there is a collision, they will silent, and after some time they will start communication. Okay, so they will okay, so what happens is that when collision is detected, a jamming signal, a powerful signal is sent the machine that detects collision, and then everyone knows that there is a collision. Okay, so what will happen if there is a collision? If there is a collision, what will happen? Okay, now everyone will wait. Let's assume that everyone waits for say 1 second and starts retransmission. Again there will be collision. Okay, if there are multiple machines have frame to send and wait for same amount of time after collision, there will be collision again, right? So what will happen? The solution now is that let different machines wait for different period of time. Okay, and that's called binary exponential back off. It means that each machine will back off for binary exponential time. It means that a number randomly selected out of a period of time, right? Okay, all right. So there is a period of, okay, so NIC chooses k from 0 to 2 raised power m minus 1, where m may be some number. Okay, and waits for it, randomly chooses out of this set, and then waits for 5 into k into this is a k number which is chosen, and 512 bit time. Basically every machine has to wait, we will pick up a number from this and wait for that period of time. So probability of collision will reduce. Okay, okay, and if again let's assume that two machines or multiple machines have start communication again, then the longer back off, then time that they will wait before retransmission happens will be longer, and so on, right? So it's very simple algorithm. Okay, so now the packet size requirement is there because of it, because this guy will come to know that there is a collision, okay, only when the first bit goes to end and it collides with the last guy. Last guy starts communication, and this collided signal comes back here, and this guy sends it. Now this is possible. It can, now suppose before this collided signal comes back and it has completed the frame transmission, then it's free. It will then it will not come to know there is a collision. So last bit of this packet which this guy is sending, let's assume this is the first bit, and sorry, this is the first bit and this is the last bit. Okay, so last bit must not be sent till the collided signal comes back, right? So it means that this frame has to be of certain length. Okay, because the speed at which you can put signals here is limited. That's called transmission speed. All right. So now from this you can derive that what should be minimum length of a packet for collision to be detected, right? So it's like this, the signal goes here and comes back, and at this point in time you can find it out. Now, so you can easily see the formula P by R has got to be greater than 2L by C. P is the packet length, this frame length. R is rate at which you will put this speed at which you can transmit these bits onto this cable. Okay, so this the last bit will go only at that point, right? This will give the time, and this time has to be greater than 2 times length, because signal has to go twice to the end and at the speed of light, right? So 2L by C. So it's very simple. Please go through it by yourself and you'll understand it. It's no big deal. Okay, so the problems were initially thick Ethernet we used, and it has all the problems that we already studied. Then we came to this model where we have a hub, and that from hub we'll have multiple machines connected. This is called start topology, right? So this is the method we use, and this was very simple. Okay, because this wire were very inexpensive, and we have hub and spoke topology, and which is quite good. Okay, so now we have this hub, and if you want to connect a machine, there will be ports here. You just take Ethernet cable from your machine and connect it here. So it becomes extremely simple thing, right? And now what happens in company is we have and one place where is this switch or router is there. From there all the wires run to every desk. So it becomes very simple. So now we have moved from this method to the method here. Okay, where you have hub here, which is nothing but a simple signal amplifier. Now if you collapse this becomes something here. Okay, and from there you run UTP cable. Okay, any question up to this point? Hello?
No, sir.
Okay, all right. So this is the method, right? I mean, you can see a hub here, which becomes single collision domain. Okay, and then so each machine is connected with pair of wires for sending signal and receiving signal, and this is nothing but a repeater. All right. Now, what is the issue here? See, what is overhead? What defines efficiency? Efficiency in general about thick Ethernet or this kind of methodology is that there's a collision. Why do you need anything to collide? And whenever there's a collision, then collision is to be detected. All the communication that happened before collision is wasted. And and more machines are there in network, more and more collisions will happen, right? More machines are connected, they will of course have data to send, and then collisions will more. So it's a wasted bandwidth, right? So inefficiency. How can we avoid collision then? Keeping Ethernet frames as same Ethernet frame. Okay, so now what we do is that in the center, instead of hub, which is nothing but a repeater, we will have a switch. This is a switch. All things remain the same. Like here, instead of hub, we have a switch. What is a switch? Switch will look at the destination address of Ethernet, destination Ethernet address, and then we'll send it to appropriate link. Okay, simple. Any question? Any question that comes to your mind? So even in this case, okay, how will anybody know that packet is for itself? This guy is sending a packet, okay, to D, for example. Okay, it will have a destination address corresponding to D. Let's assume it's a D. This is a 48-bit address. How will D know it's for itself, right? Now in Ethernet, every machine reads whatever is being sent in this kind of mechanism, broadcast mechanism, right, or thick Ethernet mechanism, or hub-based mechanism. Every machine receives that, and it checks the destination address and received packet. And if its address is of Sony, machine knows it belongs to me. This address belongs to me. Will pick up that. Okay, we will accept the packet, and all other machines will reject the packet or discard the packet. Now this was a security issue. Right? Okay, all right. So now what we do is that this destination address, now we have switch here, and this switch will know where these machines are connected and will send it to appropriate link. Okay, how does it, suppose this laptop, guy who is here goes away and his friend comes and plugs in his own laptop, then the Ethernet address changes. How will this switch know that a packet comes from this guy for your friend, for example? Then how will it know that this Ethernet address belongs to this link? Because earlier this switch has different understanding altogether. So it means that permanently we cannot create a table. Otherwise, no new user can be admitted, right? So hence, this switch has to be self-learning type. It will learn continuously. Okay, how can a switch learn that, for example, address A is A, this guy has address A, this guy has address B, this guy has address C, this machine has address D. How will it come to know that A is connected to link 1, B is connected to link 2, C is connected to link 3, and D is connected to link 4? How does it learn? Okay, that's what we'll see. So this Ethernet we call a switch Ethernet, and there's active switch at the sender. It still uses CSM HCD plus no collision. Okay, and now we have a store and forward method, right? If the frame goes from here or packet goes from here, it will be stored here. It will put into buffer, and then switch will do the processing, right? So it's called a store and buffered kind. So routers are also store and forward kind. So switches are also stored and forward. However, switches work at layer 2 address like Ethernet address. So far we have not used IP. This Ethernet, which is packet which is being sent, may contain IP. Okay, but switching is happening only at the Ethernet level here. Okay, all right. So now Ethernet address, or MAC address we call it, is used for switching or forwarding, right? So it's a plug and play and is self-learning. Okay, so I will see how can it learn. So now this is a switch. There are machines A, B, C, then A dash, B dash, C dash. Okay, you can also number them D, E, F, whatever you want, and they are connected to different interfaces, right? Okay, so A is connected at 1, then B 2, 3, A dash at 4, and so on. Okay, so all right. So now let's look at it. Now in this method, A can send packets to A dash, and B can simultaneously send packets to B dash. Only thing is, when B is sending to B dash, it will be buffered here, and will then when switch will look at the packet and find out where B dash is. It will say that yeah, it's there at port 6, then it will send it to 6 and so on, sorry, 5, and send that packet to 5. Okay, similarly B, when we are doing A to A dash, uh, when A is sending to A dash, a packet destination address will be A dash, switch will know is connected to 4, and when packet comes in here, it will look at the packet header, destination address, and send it here. Okay, that way parallel communication can happen. So it means when parallel communication can happen, then there's a more bandwidth in comparison to earlier one where only one communication was possible at a time. Okay, all right. So how does switch come to know A dash is connected to port 4 and B dash is connected to port 5? That's the question, self-learning, right? All right. So now each switch has a switch table. It will have switch table, this switch for example, and it will have a field. So now it has a MAC address of, say, MAC address of host. So this, for this machine, let's assume MAC address is A, then second machine has a MAC address of B, this 48-bit address, for example. Then C, A dash, and so on. So it has all these entries. Okay, now it will also have which interface it's connected to, right? Is connected to, say for example, A is connected to 1, but how now this, if this B is connected to, C is connected, if this information is there, then it's sufficient for routing, right? But how does it know A is connected to port 1? Because A can be switched off, or A, instead of A, some other guy can come in and then connect here, so this address could be different. Okay, it means now all this information here must be learned. And also there has to be timestamp, because this relationship that A is connected to port 1 is not permanent. It will change over time. Okay, so it means after this time, let's assume the understanding is that A is connected to 1, this will be deleted. Okay, all right, so this is a method, right? So now let's look at. So now let's assume A has a packet to send to destination A dash, where A and A dash are MAC addresses or Ethernet address. So A will create this frame and send it to switch. Okay, and it has to go to A dash, right? Now when this switch receives this packet from A, it will look at this source address, MAC address, and will enter here the MAC address, and it has come from this interface. So it will write the interface. So this packet has come from A, it will write interface 1. Okay, and we say time to live for this relationship is just 60 nanosecond or millisecond or whatever. Okay, so this learning is done. Now this guy doesn't know where A dash is in the beginning, right? When everything is starting up, it doesn't know. What will it do? If it knows that A dash is connected at port 4, it will send the frame, but it doesn't know, right? So what it will do is that it will broadcast it to all. Okay, all right, so initially it's like this. Okay, I will repeat. So initially as soon as this comes here, it will come to know about this relationship, but this doesn't know where A dash is. It will look at A dash, then it will flood, it goes everywhere. Okay, now A dash will receive it, because it, C will receive it, B, all others will discard the packet. A dash once receives it, what it will do, in general it has to respond back, right? Because communication is usually not one way, it will send some kind of acknowledgement. When it acknowledges it, this switch will come to know that A dash is connected at port 4, and as this communication goes on, then switch will learn about who is connected where. Okay, all right, so this is the method. Now this learning can happen even if switches are connected in this manner, right? These are switches, they are connected to each other, right? And now this learning will happen hierarchically, right? So initially, for example, A is sending message to H. First S1 will learn that as soon as it receives frame, it will learn that is connected to the particular, A is connected to the particular port, but it doesn't know where H is, so it will broadcast it in all directions. Okay, S4 will know that A is connected onto this port, it will know this, this learning will go into table, and then it will broadcast to everywhere. Okay, and finally it will reach H, and when H responds back, all switch will know where H is. In this way self learning can happen. Okay, all right, so this is a very small institutional network. These are the switches. Okay, so broadcast domain here is as long as we have switches. For example, here even now broadcast is happening here. Okay, now in order to restrict the broadcast ranges, we will have to connect it to a router. Okay, we'll study that concept later. Okay, so now the packets, when we say switches versus routers work at layer 3 IP layer, switches work at data link layer. Both use store and forward mechanisms, and we'll see in between the packets go only to physical layer, data link layer. Oh, sorry, if there is a switch, packet don't go to IP layer, it gets switched at link layer. And if it's a router, like router is shown here, then it go to IP layer also. Okay, all right. Now what we can say is that now L2 and L3 have to interact with each other. Okay, note that broadcast domain, as long as whether it's a switch or Ethernet, broadcast domain is all the nodes in that. So as we have seen here, you know, this is a switch, this also a switch, this also a switch. What then so in order to learn the tables, the broadcast has got to be there here. So it means that initially this guy is sending packet to even this guy, and switch doesn't know, it will send it in all direction. This, it means that this machine A is connected, Ethernet is connected, which port in individual switch will go to everywhere. So this is a broadcast domain. Okay, so now we can connect these individual LANs either through a switch or through a router. Okay, all right. So now we can connect. So what if you want to restrict the broadcast domain, then we have a router. Then we'll have to go to layer 3. So this becomes a broadcast domain. Okay, similarly this becomes a broadcast domain for this net, and then this is a router. So we go to layer 3 here and transmit packets. Okay, so this is another view. Okay, this is one organization, it will work on within the organization, a small organization, it will be Ethernet. All the switching will happen using layer 2 or Ethernet address. Only if this guy, some guy has to send it to outside world, then it will go to interface router. Like, you know, when we study DSCP, one of the parameter which DSCP gives is interface router's address, right? So now it can go to from one domain to another LAN, and within LAN it will transmit using layer 2 address, then it goes to interface router, and then so on. Okay, so this is a normal method. So I will repeat this another 1 minute and we'll close then. So now this guy has to send a packet, IP packet. Okay, this IP packet, it will put IP packet within an Ethernet. Okay, and here the destination of address of that ether in that local area network will be this one, corresponding to Ethernet address of this router. Okay, so now this packet will go at layer 2. So all these nodes will do layer 2 switching here. Once it receives, it will remove the Ethernet. Okay, and then use the routing IP address and to know which link to send it to, and then it will put again it into corresponding layer 2. Let's assume this again is Ethernet frame, and send it to this one. This guy will remove Ethernet outer one, get the IP, and will know where to send. It will have IP address of this one, and from we will also come to know Ethernet address of this one, and then again create a frame. In that frame, destination address will be corresponding. So now this frame, Ethernet frame, will reach here, then it will remove Ethernet outer frame and then get the IP packet, and so on. So in this way it will move. Okay, all right. So this is, so we have routers always at the edge of local area network, and you know, so that way packet can go from one institution to another institution to third institution and so on, right? So like this here is shown. All right. So what you studied is Ethernet is de facto technology, layer 2 technology. It has evolved up to 100 gigabit or even more. Initially we had switched Ethernet, shared Ethernet, And from that we came to switch Ethernet is highly efficient because no collision. Although we use broadcast mechanism for learning, but that can also be optimized which by putting routers at appropriate places, right? Switch Ethernet is self-learning, no collision, star cabling. Okay, all right, that's all. Any question? No? So I'm very fast because I don't have time to go through it in detail. I hope please go through slides and you will understand it. Okay, it's available everywhere. I mean this content what I have taught is there everywhere. Okay, all right.